So in this section, we're going to investigate a tool that helps us understand graphing better when we're working in the XY plane. And this tool is called the distance formula. There's a handout posted in Canvas that has the statement of the formula, and it also has the exercises that we're going to work through together today. And before we get to the handout problems, I just want to talk a little bit about where the distance formula comes from. So suppose we have 2 points in the XY plane that I labeled x1, y1 and x2, y2. So I labeled the x and y coordinates of each of those 2 points. And suppose we want to figure out how far those points are apart from each other. So I'm going to draw a line connecting them, and I'm going to label this D for distance. Suppose we want to figure out the distance between those 2 points, the length of this line, by working with the coordinates of those points, by working with the values of the x and y coordinates. So what we can do, and the way we get this distance, is we actually can think of a certain triangle, a right triangle in this picture. And from the way at least my points are arranged, I can draw a right triangle like so. And I'm going to label the 2 other sides of this right triangle A and B. And there's a theorem from geometry called the Pythagorean theorem that we're going to use to obtain our formula for the distance d. The Pythagorean theorem tells us that the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. So in this picture, the Pythagorean theorem would be a squared plus b squared equals d squared. If we know the lengths a and b, we can figure out the length d using this formula. And so how can we do that? Well, how do we get the length a and the length b from the coordinates of these 2 points? Now, at least the way I've drawn my picture here, I can see the x-coordinate of this first point corresponds to a x1 value here on the x-axis. The x-coordinate of my other point, I'm going to label here as x2. And on the y-axis, I can label right here as my y1. And corresponding to the other point is y2. I can use the x and the y coordinates to describe both the lengths a and b in this picture, because the length a is the same as the distance from x1 to x2. That distance in terms of the x-coordinates is just the larger x-coordinate minus the smaller x2 minus x1. That's equal to the length a in this picture. And the length b, if you imagine moving sideways over to the y-axis, the length b is the same as the distance between y2 and y1 on the y-axis, and I can get that length by subtracting the larger y value minus the smaller. So y2 minus y1 is a way to calculate that length b. So I can figure out a, can figure out b, and then we're going to use the Pythagorean theorem to get the d distance from the a and the b. Now this picture depends on the points lining up in a certain way. The formula that we obtain in general works no matter how the points are lined up. So let's go over to the handout now, and I basically have most of what we were just looking at here, and I'm just sort of summing things up. So d squared is equal to a squared plus b squared. but a can be replaced with x2 minus x1, y, or b with y2 minus y1. And so I have d squared equals this whole mess of stuff on the right. To get d alone, to solve for d, I take square roots. When I take square roots, I'll get d is radical the square root of x2 minus x1 squared plus y2 minus y1 squared. And that's what we call our distance formula. And we're going to go ahead and apply that to some problems now to see how this thing works. And so I have on my handout, I have several exercises, and I've gone ahead and copied those on a separate sheet of paper. And just to get us started, I want to go back to just really the bare essentials here. So we had 2 points. We wanted the distance d. That distance d is given by this formula on the right. Now let's go ahead and apply this to a particular problem. Suppose we want to find the distance between the point 0, 8 and 6, 16. So we want to think of one of these points as my x1, y1 point, and one as my x2, y2 point. So I'm going to then plug into our distance formula. The distance is the square root of x2 minus x1 in parentheses squared plus y2 minus y1 in parentheses squared. So, you know, in this form, it's quite a big mess now, right? And I think it's helpful to keep in mind, though, that it really grew out of just this basic Pythagorean theorem relationship, this relationship between the sides of a right triangle. Okay, so now back to our problem. I'm going to plug in. So d is the square root of, inside parentheses I write x2 minus x1. My x2 coordinate is 6. My x1 coordinate 0, so 6 minus 0 in parentheses squared plus, and then in the second parentheses I write y2 minus y1. 16 minus 8 in this case, squared. And what I get is 6 minus 0 is 6, so I have 6 squared, plus 16 minus 8 is 8, so I have 8 squared. And now a really important thing to know about working with square roots is when you're adding two quantities, you cannot take square roots separately. So I can't take the square root of 6 squared or the square root of 8 squared. The answer is not going to be 6 plus 8 here. I have to square those numbers first. So 6 squared is 36, 8 squared is 64. And I have to complete the addition. 60, 70, 80, 90. It comes out real nice here, actually. I get radical 100. And then I can take square roots. And here, 100 is a perfect square. It's 10 squared. So when I take radical 100, I get 10. And 10 units is exactly the distance between those 2 points. Now, we're going to do a few more where we look at slightly messier situations. So let's find the distance between 3, negative 2, and negative 4, 5. If it helps, you can always label one point as x1, y1, the other is x2, y2. Doesn't matter which one you call x1, y1, which one you call x2, y2. Could do it in either order. The formula will come out the same in the end here. So my distance is square root of, I'm not going to recopy the formula each time. It's x2 minus x1, second x coordinate minus the first. So I have a negative 4 minus 3 in parentheses squared plus, now I take the y2 minus y1. you got to be careful with minus signs. Here I have 5 minus a negative 2. So there's a double minus sign inside that second parentheses with the second squared parentheses, because I have a minus sign from the formula, and I also have a minus sign from the negative 2 coordinate. So what I got here inside the square root, negative 4 minus 3 is like a negative 4 plus a negative 3 is negative 7 squared, plus 5 minus a negative 2, minus a negative 2 is like plus 2. 5 plus 2 is going to be positive 7 squared. Just want to write this on the side. 5 minus a negative 2 is the same thing as 5 plus 2. That's where that positive 7 came from, right there, right? And now I have a negative 7 squared. Well, negative times negative is positive, so it's positive 49, plus positive 7 squared is also positive 49. I get 49 plus 49, which is radical 98 when I add those together. And now I want to take square roots. Now here, I want you to try to simplify the square root if possible, algebraically. And we can also talk about decimal value for the difference. If you stopped at this point, you really just about got it. You did just fine. But there is some simplifying to the square root that we can do. So I want you to think about how we could factor 98 as 2 times 49. And that's nice because 49 is a perfect square. I can take this apart as radical 2 times radical 49, which is radical 2 times radical 49 is 7. The 7 is now outside the radical. 2 is inside. Traditionally, when we have a number outside times a number inside, we write the outside number first. 7 times radical 2 is my simplified radical form of that distance. And I'm also going to get a calculator value here. Take square roots. Yeah, that's about approximately 9.9. It's actually very close to our other distance. So the actual distance I see a little bit better from the decimal value than I do from the 7 radical 2 value. I can also see that 9.9. That makes sense that that's really close to 10 because I'm taking the positive square root of 98 very close to the positive square root of 10, right? Just slightly smaller as we see from our decimal. Okay, let's do another problem here. We're just going to plug in, and I'm not always going to label the points from now on with x1, y1, x2, y2. Let's go ahead and calculate our distance here for these 2 points, negative 6, negative 2, and 6, 2. So I'm going to take my difference in my x's. So 6, I got 6 minus a negative 6 here, squared. So there's a minus sign from the minus sign on that negative 6 coordinate, and there's also a minus sign from the formula. Plus y2 minus y1, 2 minus a negative 2 squared. So what do I have here? 6 minus a negative 2 is 6, I'm sorry, 6 minus a negative 6 is 6 plus 6, or 12 squared, plus 2 minus a negative 2 is 2 plus 2, or 4 squared. So I have the square root of 144 plus 16. Now I gotta resist the temptation to take square roots separately. I cannot do that here. I have to add them together. So 144 plus 16 is 160. And then try to simplify that square root if you can. Here I see that I have a 16 times 10. So when we're multiplying, we can take the square root separately. So I can write that as radical 16 times radical 10. Then I can take the square root of 16, because that's 16 is a perfect square. Radical 16 is 4, but the radical 10 stays alone. And that's, I would say that's simplified because 10 can only be factored as 2 times 5. I cannot get a perfect square factor out of 10. So there's my distance for radical 10. And if we want a decimal here, I get that that's about 12.6, 12.65. Oops. All right, so I'm going to stop our introductory video here. We're going to do some more distance formula problems in the next segment.